Now, so let's look at the problem. Let T be the solid. And we're told solid is 1 less or equal to x squared plus y squared plus z squared less or equal to 4. And z is greater than or equal to 0. And we're asked to find the integral. What does this notation tell you? The boundary of the solid of something. This is a vector valued function. What gives it away that it's a vector valued function? Yeah, the ijk. That's okay. It's a vector, and there's functions attached to the directions. Dot n. This, when you see a vector valued function dot n, that's a flux through the surface. So you're finding flux through the surface of the boundary of the solid. When you see a solid, you see flux through the surface of the boundary of the solid. What's the tool? Gauss's divergence theorem. Okay, so this is a divergence theorem problem. Divergence, how did we know divergence? Well, big clues, there's a solid. That's a big clue. You apply the divergence theorem, so you took the divergence, and so you took the partial derivatives. The divergence one is a nice one. So you have your m and p, partial m partial x, partial n partial y, partial p partial z. You take your partial derivatives and you get down to 4z. Now the hardest part would be like, well, you actually have to integrate this or figure out what it is. So the shape is sort of it's a half a sphere with a smaller half sphere dug out. I think of it as a half a cantaloupe. That's not a technical math term, but that's just sort of like to visualize what's going on. And so one of the things that often happens with the divergence theorem, with Stokes theorem, is that you embed inside of it problems that use tools. So you've been inside of it things such as spherical coordinates in this case. Stokes theorem sometimes embeds inside of it things like polar coordinates. So be ready. So the nice thing is in spherical coordinates, well, why do we choose spherical coordinates for this region? Because you have spheres. And in spherical coordinates, this is very simple to describe. The 0 to 2 pi for theta is just a reflection that says, oh, we go all the way around in the z direction. So that's why we go 0 to 2 pi. We have that beautiful symmetry around the z-axis. 0 to pi over 2 for phi. Remember, phi is straight up, so pi over 2 brings you down to the xy plane. And then 1 to 2, that's just between your two spheres. And so you update, your 4z comes 4 rho cosine phi. You've got your rho sine of phi, d rho d phi d theta, right? And then you just break it up and life is not too bad. All right. So, a little bit of work, but not too bad. Okay. Well, our thought for the day back from the 80s, Buckaroo Banzai. No matter where you go, there you are. And, well, it's hard to argue that. It's true. But I like to think of it in sort of our context for, who's taking the test? It's going to be you. Make sure you put yourself in the best place. It's not something miraculous isn't going to happen where you show up in the final and be like, then all of a sudden I remember everything. It's what you put into it and who you are before you show up at the final. That's what's important. And so put in the time. Be a good person. No matter where you go, you have to be around yourself. Be nice. All right. Well, I guess today is this one slide. And so we'll talk about the right-hand side in a second. The left-hand side, what we've been talking about in the last few weeks falls into what's known as vector calculus. But really it's just, let's do variations on the fundamental theorem of calculus, because they all have a similar flavor, which is to say we're looking at integrals and saying how do we evaluate them. And in particular, we say, oh, there's something about the boundary. We can sort of do something on the boundary versus something in the interior. So we started with line integrals. So we said, well, the integral along a curve of gradient of f dot TdS, well, that says you're working with a gradient of f. That's a conservative function, which means there's a potential function. So essentially there's f is its, antiderivative, if you will. And you evaluate it at the endpoints, which is really the boundary of the curve. Then we went and talked about Green's theorem, which says, well, if we have a curve that's closed, we can compare an integral on the boundary to an integral over the interior where we have derivatives involved. And I said, well, actually, you can go and do this in 3 dimensions. That's Stokes Theorem, but the same concept applies. And then he said, well, we can also do things with Gauss's divergence theorem where we can compare an integral on the boundary of a solid of the flux to an integral over the interior of a derivative, in this case, the divergence. So in all cases, sort of on this right-hand side, is we're looking at the boundary of something, and on the left-hand side, we're looking at an integral of some form of derivative in the interior. So there's this unifying theme. Now there's a couple of notes here you may notice. What does this BYOS stand for? Yeah. For most Stokes theorem questions, it's usually the fastest way to go. If they give you a surface and you say, I could do better than that surface. And so you might say, well, what's an example? Well, maybe they give you a piece of a cone, right? And they say, hey, what if I have a cone coming down and my boundary is just the top part of the cone? What can you do instead of working with the cone? So what's an option? Yeah. Instead, you can say, look, don't work with the cone. That's complicated. Make it flat. Make it a disk. Why? Well, because that's simpler. And our goal in a lot of math is, hey, let's make things simpler. And oftentimes, if you make things simple enough, you might even be able to do it. It's a crazy idea, but it just might work. Well, what does this one up here mean? Bring your own curve. The same philosophy. It's not a coincidence. It says, hey, if I have a conservative line integral, I really just need to have 2 things that meet at the same endpoint, and life is good. So be open to that. So for Stokes' theorem, almost always you should look for make it a simpler surface, because then life is easier. All right, let's talk about identifying. How do you know what to use and when? So the first one, a conservative line integral. What are you looking for? I'll give you a spoiler. It's kind of written down here. Yeah, you got a curve with different endpoints. Now, be careful. If I have a curve with different start and endpoints, can I always apply this? I'll give you a hint. I said the word be careful. No. Okay, so let's talk about that, because I just want you to be open to that possibility. So let's suppose we make up a problem. All right. We'll try to keep life easy, because I'm an old person, so it's hard to do things on the fly. Let's pick a point. Anyone have a favorite point?
0, 0.
Are you sure? 1, 2. Okay. 1, 2. Here we go. Here's a point. 1, 2. All right. Does anyone have another point? 5, 0, I think someone said. And even if they didn't, I'm going to pretend like they did. Okay, 5, 0. All right. So here we have 1, 2, and here we have 5, 0. And now let's put a straight line between them. And here's our curve C. I'll put a little arrow here. And I know it looks like it's not a straight line, but pretend like I could draw a straight line. And I asked you to find the following. Find the integral along this curve of 2x plus 5y dx plus 3x minus 4y dy. All right. Is this conservative? Now, it looks like it could be, right? It has the right form. So this expression looks like it could fit into this. So keep in mind, this can be written in many different ways. It could be, but is it here? No. How do you know it's not? I mean, you can compare derivatives. You can also say, well, if I were to build up, if I integrated this term with respect to x, I'd get 5xy. If I integrated this term with respect to y, 3xy. Does 5xy match 3xy? No, there's not consistency, not conservative. So, can you find this line integral? Yes, but not using the conservative line integral tool. So what tool do you do? Wait, what's the tool? Parametrization. Ah, nice. Good. So you have to do a parametrization. Parameterization, I don't know. Every time I type this into a computer, it always says it's not the right spelling. So it's probably not a real word. But let's say it is. Parameterization. All right, so we have to parameterize the curve. Do we have the technology to do that? Yeah. Are there many parameterizations? Yes. In fact, there's infinitely many parameterizations. Which ones do we pick? Easy ones. Right? Remember, we like ourselves. And because we like ourselves, we're going to try to keep it easy. So, with that being said, does anybody have a suggestion for how we actually find this parameterization? What if I said this curve was just part of a bigger line? Could you find that line? You have 2 points. What's the slope of this line? Down 2 over 4. Slope is negative 1/2. So y equals negative 1/2 x plus something plus what? Well, what happens when I plug in x equals 5? What should come out? So when I plug in 5, I get negative 5/2. What do I need to add to get to 0? 5/2. Now, if you had that, could you find a parameterization? What? I thought I heard an answer over there. Okay. It's a good thing we're practicing this, right? What's the parameterization that we can pick? Well, how about we pick x is t. What would y be? Negative 1/2 t plus 5/2. Now, is this our parameterization? And why not? We also have to specify where t runs from. Where does t run from? 1 to 5. Okay. Is this our parameterization now? Yeah, it's good. Are there other options? Yes. Do we like this? Yes. Why do we like this? It's simple. Okay, so now can we find this integral? All right. How do we do it? Integrate. What will be our bounds? 1 to 5. So everything becomes our parameterization. Where we see x, what do we put? Where we see y, what do we put? Negative 1/2 t plus 5/2. Where we see dx, what do we put? 1. The derivative of x. Where we see dy, what do we put? Negative 1/2. All right, so it becomes 1 to 5. And then we just start putting things in. 2 times t plus 5 times negative 1/2 t plus 5/2. That's the 2x plus 5y. dx is going to be 1 plus 3 times t, that's our x, minus 4 times minus 1/2 t plus 5/2. And then the dy minus 1/2, and all of that dt. Should we finish it? Yeah, might as well. In for a penny, in for a pound. 1 to 5, okay, we group, we have our, I'll change colors for a second here. We have 2t minus 5/2 t. Then here we have 3t plus 2t, right? 3t plus 2t times minus 1/2. So this will become minus 5/2 t minus 5/2 t plus 2t, all together giving us negative 3t. Okay, that's our constant. Now, sorry, that's our t. We have 25/2. And then over here we have minus 4 times minus 1/2, which is 2, times 5/2. So that would give us 5. So that's minus 4 minus 1/2 times 5/2. Which, by the way, is the same as 10/2. So it'd be 25/2 plus 10/2, 35/2. Yes? And so this becomes minus 3/2 t squared plus 35/2 t. You evaluate from 1 to 5. You get out a number. Now you can say a little bit better than that. 5 squared is 25. 1 squared is 1. So this becomes 25 minus 1, which is 24. 35/2. 5 minus 1 is 4. 2 goes into 24, 12, so this is minus 36. 2 goes into 4, plus 70 equals 34. There we go. I went a little bit fast at the end, but it's just evaluation. All right, so if you have a line integral, it may not be conservative, but that's okay. We can still do it. So that's what you're looking for when you're looking at line integrals. What are clues for Green's theorem? What are you looking for? Closed curve. You might also see sometimes they've dropped the word circulation on an exam. And circulation is just a way of saying integrating f dot t on a closed curve. That's circulation. The other thing, of course, for Green's theorem, be in the plane. And one of the things I didn't specify here is check your orientation. Because everything here has orientations. What happens if your orientation is the wrong way? Yeah, you flip the sign. So just make sure your orientations are going the right way. Okay, so Green's theorem is pretty clean to find. You're just looking for anything that looks like an integral of the form, m dx plus n dy on a closed curve, and you can apply Green's theorem. So it's almost foolproof. Unlike conservative line integrals, you have to kind of check. And the reason you have to work harder for conservative line integrals is we're sort of going in the way of finding an antiderivative, whereas for Green's theorem, we go in the way of finding a derivative. Antiderivatives hard. Derivatives, easy. So that's why Green's theorem is a little bit funner to apply. All right, Stokes theorem. What are things we look for? Closed curves in space. We're in 3 dimensions. What else are we looking for? Yeah, if you see a curl somewhere, that's a pretty strong indication that it's the Stokes theorem. Now, sometimes they may not say it, but if you see a curl like, they're trying to tell me Stokes theorem. We mentioned closed curve. What else could we have? Surface with boundary. Sometimes they will only give you the curve, and then you have to provide the surface. Sometimes they'll give you a surface, and then you probably have to say, you gave me a bad surface. Let me give you a better one. Okay. Gauss's divergence theorem. Oh, yes, I should be careful here. So Stokes theorem deals with a surface integral. Can every surface integral use Stokes theorem? No. So not every line integral can be a conservative line integral. Not every surface integral, you're integrating something which is a curl. What happens if you're integrating something that's not a curl? What do you do? So what happens if you don't have Stokes theorem? You remember the formula? If you integrate on a surface and it's some function, I'll call it h dot n, this is not from a curl. What can you do? Right, so someone started saying things. So let's say this, here's our h, m, and p. And we'll say that G is the surface Z equals f of x, y over a region R. Then what do you do? What's the formula? Negative m fx minus n fy plus p dA over R. So, not every surface integral you can apply Stokes. The problem is, it's the same issue I mentioned before. Essentially, it's easy to go in one direction. So it's easy to go in this direction, from right to left. It's hard to go from left to right. So be careful on how you're applying things. Okay, so Gauss's divergence theorem, it's the easiest to find. You're basically looking for one of two things: a solid or a closed surface, a surface without a boundary. So if there's a surface without a boundary, what can you do? You can feel the surface. It has an interior, and you just say, my solid is whatever's on the inside. Now for Green's theorem, we are allowed to have holes. In Gauss's divergence theorem, are you allowed to have holes? So in particular, what if I have like a donut? Does Gauss's divergence theorem still apply to donut shapes? Yes. Yes. Holes are okay. You just need a solid. In fact, we did a donut last time. You may remember we had a cylinder. This was our example at the very end of last time, with a smaller cylinder drilled out, which was just another way of saying, it's like a donut, but easier to describe. So yeah, holes are allowed, no problems. All right, so that's the 4 things you should be able to identify. You kind of know 2 of them are coming, so be open to those 2. Any questions on identifying things? So if you're out walking around and you'd be like, I recognize that. That's a Stokes kind of thing. Or like, aha, I see that one. That's like a divergence kind of thing. Yes? You can do it? All right. Should we try a problem? So, let f be minus 2yi plus 2xj plus xy plus z squared k, and let S be the surface, x squared plus y squared plus z squared equals 9 with z greater than or equal to 0. Find the integral over the surface S, because S is the surface, of this, whatever this means, dot n dsa. What's our tool? How do we know it's our tool? What are some clues? We see a curl. That's the clue. This is a cross, del cross f. This is curl. Curl tells us what? Stokes theorem. Is there anything else telling us Stokes theorem? There's a surface. Does our surface have a boundary? What does our surface look like? Is it a sphere? It's a half sphere. So in our case, what's our boundary? So our boundary is this circle in the xy plane. So there's our boundary. And then our actual surface, it's a bubble. Now, if we were doing this on a test, we could either say, look, I can apply Stokes theorem and do an integral on the boundary. I could try to do this integral straightforwardly. There's no really bizarre functions. But on a test, what would we think to try? Someone is like bringing modern interpretive dance, like, zoom. I like that. What's this indicating? Yeah, we're going to deflate the balloon. All right. Now, one thing is technically missing from this. What's missing? This problem is actually not complete the way it's written. I forgot to write something down. What's missing from this problem? Orientation. Your problem has to have orientation. Either the surface has to be oriented or the boundary has to be oriented. And this one omitted that. Let's orient something. Let's orient our boundary. And just because we like positivity, let's make things upward pointing. End of the semester, things are looking up. Okay, so we deflate our balloon. So our surface is now flat. We'll call this new surface a name. What would you like to call our new flat surface? I think someone said Paul, but that seems kind of a long name to give it. We could call it T. I don't know. What's the normal for our new surface? Paul, shorthand T. Yeah, it's a vector that points straight up. So n equals k. So we can say, hey, good news. From bring your own surface, this is the same as the integral over t del cross f dot k. All right, well, what's del cross f? Oh, we've got to actually do it. It's not, unfortunately, with cross product, It's not one of those things you can usually do in your head. All right, so we write things down. We have our I, J, K, our partial derivatives. Since we know there's a Stokes problem in our future, we want to get good at taking our curl. 2i minus 2i plus 2x, xy plus z squared. Now, do we have to work the whole thing out? Which part do we need? The k part. So we're just going to be a little bit something, something. Now k. K, partial x of 2x, 2. Then we have the other direction, subtract partial y of minus 2y, minus 2. Okay, so what happens to this curl of f dot k? What does it become? Zero, 0, 4, right? Because this k is really 0, 0, 1. So we get 4 DSA. That's pretty good. How does one find such an integral? Yeah. Now you're probably like, oh man, is it going to be this straightforward? I doubt it. They might make you work, but they won't make you work too hard. So the area of our surface. Now, which surface? Our half sphere or our deflated disk? Of Paul, our deflated disk. Okay, so what's the area of that disk? It's a circle. Did we say the radius? Radius is 3. So how much area is there? Yeah, 9 pi. 4 times pi r squared. So this gets us a grand total of 36 pi. Well, so that's with bring your own surface. Should we do it with as a line integral or should we do something else? Are you convinced? All right. So for the next one or two, we're not going to do the whole problem because we don't have time, but I just want to say, suppose we see this problem, what do we do? So we have given a vector valued function f. We're told C is a curve resulting from intersecting. Now, by the time you hit this phrase, a curve, what do you know it's not? What is it not? It's not Gauss. Because what does Gauss deal with? Solids and surfaces. So it's probably not Gauss's divergence theorem. So C is a curve, and we're finding integral along a curve intersecting x squared plus y squared equals 1 with the plane x plus z equals 1, oriented counterclockwise when viewed from above. Find the integral of C of f dot t ds. What's the tool we should be pulling out? Stokes theorem. Okay, so what's the issue here? When we look at this one. Stokes is the correct thing. What's the surface? Just visualization. X squared plus y squared equals 1. What does that look like? Cylinder. Circle if you're in the xy plane, but we're in 3 space. So you'll notice, well, there's no z. That just means you copy it straight up and down. So you have this x squared plus y squared equals 1. Goes straight up and down. Okay, so we have this cylinder. X plus z equals 1. What is that? It's a plane. The plane. You're too young to know this. There was a TV show, Fantasy Island, way back in the 80s. And it always started with someone going, the plane, you know, bringing in that week's special guest stars. All right. Where is our plane? X plus z equals 1. Well, it's not too hard to plot a couple points. It looks like a line in the xz plane. And then what do? You copy it back and forth. So when you intersect, the intersection is this sort of, roughly speaking, an ellipse. So if you want to apply Stokes' theorem, what do you need to put in? We need a surface. We already have a curve. We're missing a surface. What surface do we put in? We use the ones that were used to make it. So we say, we're using our surface is this x plus z equals 1 for the portion which we need. And then we go from there. Okay, one more. We won't do it, but which tool do we need? Let Q be the solid. Okay, instincts? Yeah. Described by, we have a sphere, we have a cone, we're finding the integral on the boundary of the solid. So it's flux through a solid of a flux through the surface of a solid, Gauss, right? After you see these for a while, solid, Gauss. Surface with boundary, Stokes. It becomes automatic. All right, that's it for today.